There is a vault somewhere in the American Midwest that is missing roughly 1.5 billion pounds of ancient treasure.
Yeah, it's a massive amount.
And at the exact same time, there is this microscopic, highly efficient assassin just quietly waiting on the unlacquered brass doorknobs of 19th century buildings all over the world.
Just hiding in plain sight.
Right. And sitting in your pocket right now, or humming inside the walls of the room you're sitting in, is a star-forged metal that currently holds the key to unlocking the multidimensional math of the quantum realm.
I mean, it sounds like the setup to a science fiction novel, doesn't it?
Totally.
But it is entirely demonstrably real. And the wildest part is that all three of those things, the missing treasure, the biological assassin, and that quantum key, they're all exact same material.
Which brings us to our mission for today's deep dive. We're going to take something that you see every single day, something so utterly ubiquitous that it has become completely invisible to you, and we are going to fundamentally transform your perception of it.
We're talking about copper.
Exactly. So if you have a handful of loose change nearby, or a spare piece of electrical wire, I want you to literally hold it in your hand while we talk, because by the end of this deep dive, that mundane piece of reddish-brown metal is going to feel like an alien artifact.
It really is the absolute definition of hiding in plain sight. I mean, we literally frame our understanding of human history around it, the Copper Age, the Bronze Age.
Right.
But very few people actually understand the sheer physical and biological absurdity of what this element actually is, like how it operates inside our own bloodstream or how it behaves at the absolute extremes of the universe.
So let's start at those extremes. Because if you want to understand why humans have been so obsessed with copper or how it acts as a molecular weapon, you have to understand its birth.
Mm-hmm.
And the truth is, the copper sitting in your hand right now did not spontaneously form on this planet.
Mm-hmm.
Earth is entirely incapable of creating it.
Yeah, Earth doesn't have anywhere near the thermodynamic pressure required for that.
Not even close.
To find the origin of copper, you really have to look out into the deep cosmos, the cosmic origin of heavy elements, specifically things like copper, silver, and gold. It remains one of the most intensely studied phenomena in astrophysics right now.
Okay, let's break down the mechanics of that. When we talk about a star forging an element, I think most people have a vague understanding of nuclear fusion.
Right, like hydrogen fusing into helium.
Yeah, exactly. Hydrogen into helium, helium into carbon, and it releases light and heat. But that process hits a hard wall, doesn't it?
It hits a massive thermodynamic wall at iron.
Oh, wow. Why iron?
Well, for most of a star's life, fusing lighter elements together releases energy, and that outward energy perfectly balances the crushing inward force of the star's gravity.
It's like an ongoing explosion pushing against the weight of the star itself.
Exactly. But once a star's core fuses into iron, the math completely flips. Fusing iron doesn't release energy, it requires energy.
Oh, so the engine just stalls out.
It stalls instantly. The star loses its outward pressure, gravity wins, and the core collapses in a fraction of a second. This often results in a massive supernova.
So if normal fusion just stops at iron, which is atomic number 26, how do we get to copper, which is atomic number 29?
Through a really wild mechanism called the neutron capture process. And this is where the astrophysical environments get truly chaotic.
Chaotic how?
Well, imagine the core of a dying star or the catastrophic collision of two neutron stars. In those specific environments, you have a massive, incomprehensible flux of free neutrons just flying around at relativistic speeds.
And because neutrons don't have an electrical charge, they behave completely differently than protons or electrons.
Precisely. I mean,
Right.
if you fire a positively charged proton at an atomic nucleus, the positively charged protons already inside that nucleus will repel it, repels.
Right, it bounces off.
But a neutron is totally neutral. It acts like a ghost. It bypasses the electromagnetic force field entirely and just slams directly into the nucleus, getting absorbed. Or in astrophysics terms, it gets captured.
So you basically have this iron nucleus sitting there, and it just starts swallowing free neutrons, getting heavier and heavier.
It gets heavier, yeah, but adding neutrons doesn't change what element it is.
Because an element's identity is dictated strictly by the number of protons.
Exactly. However, when a nucleus absorbs too many neutrons, it becomes highly unstable. It wants to find equilibrium, so it undergoes something called beta decay.
Beta decay,
Yeah. One of those newly captured neutrons spontaneously decays, transforming into a proton, and it spits out an electron in the process.
Wait, and the moment that neutron becomes a proton, the atomic number goes up?
Yes, the atomic number ticks up. So through this rapid or slow capture of neutrons, what astrophysicists literally call the R process and the S process, the atom slowly steps its way up the periodic table.
From iron to cobalt to nickel and eventually to atomic number 29, copper.
Exactly. And tracking exactly where and when this happened across the entire history of the universe is a massive ongoing project today. Scientists are essentially trying to map galactic chemical evolution.
Which sounds impossible. But doing that requires incredibly complex models of starlight, right?
It requires deciphering the light spectra of distant stars. Every element absorbs and emits light at very specific wavelengths. It's like a barcode. By looking at a star's light, we can read its barcode and see exactly how much copper it contains.
But I was reading in the sources that for decades, the way we read those barcodes was, like, fundamentally flawed.
It was. Astronomers used to rely on 1D LTE models.
And LTE stands for local thermodynamic equilibrium.
Right. It essentially forced the math to pretend that a star was this perfect, static, unmoving sphere of gas with perfectly uniform layers. It was mathematically convenient but logically absurd.
Because a star isn't static. It's a boiling, chaotic, violent explosion held together by gravity.
Exactly. It is a turbulent mess of convection currents and radiation. So modern astrophysics has shifted to 3D, non-LTE models.
Which I assume require massive supercomputers.
Oh, absolutely, because they don't assume equilibrium anymore. They calculate the chaotic, three-dimensional movement of stellar plasma. They factor in highly specific variables like hydrogen collision rates.
Wait, what does that mean in this context?
It literally means calculating how often hydrogen atoms are violently slamming into copper atoms within the stellar atmosphere, because those collisions physically alter the light barcode that we eventually see on Earth.
Oh, wow. So by taking the mathematical training wheels off, they get a much more accurate picture of stellar abundance.
They do. They can look at a star that is 10 billion years old and a star that is 2 billion years old, apply these 3D non-LTE models, and map exactly how copper was distributed across the Milky Way over eons.
It's basically galactic archaeology. And it tells us that billions of years ago, through violent neutron capture, copper was forged, scattered across the vacuum of space, and eventually coalesced into the swirling dust cloud that became Earth.
It's incredible.
Which brings us from the galactic scale all the way down to the subatomic scale. You mentioned copper as atomic number 29. We need to look at its atomic architecture because this is where its seemingly magical properties originate.
Right. Atomic number 29 means 29 protons in the nucleus, surrounded by 29 electrons. But, physics isn't just about how many electrons you have, it's about where they live.
The shells and orbitals.
Exactly. Electrons reside in specific shells and orbitals around the nucleus. Copper's electron configuration is argon 3d10 4s1.
Okay, let's translate that for anyone who hasn't looked at a chemistry textbook recently.
Fair enough. The argon part just means copper shares the same stable inner core of electrons as the noble gas argon. That part is pretty boring. The real magic happens in the outer shells, the third and fourth orbitals.
The third orbital is completely full, right? It holds exactly 10 electrons.
Yes. Now, a fundamental rule of quantum mechanics, the Pauli exclusion principle, states that when two electrons share an orbital space, they must spin in opposite directions. One spins up, the other spins down.
And because the third shell has exactly 10 electrons, every single one of them has a dance partner.
They are perfectly paired up. And because moving electrical charges create magnetic fields, an electron has its own tiny magnetic moment. But since every electron in copper's third shell is paired with another electron spinning in the exact opposite direction, their magnetic fields perfectly cancel each other out.
So the net charge is zero.
Net zero.
So the inner shell is magnetically neutral. What about that lone 4s1 at the very end?
That is the single lonely valence electron. It sits super far away from the nucleus, and it is very loosely bound. When you put a bunch of copper atoms together to form a solid piece of metal, those electrons essentially just abandon their parent atoms.
They just detach.
Yeah, they detach and form this delocalized charge C. They just flow freely through the metallic lattice like water moving through a sponge.
And this combination, the perfectly paired inner electrons and the free-flowing outer electrons, creates a physical phenomenon called diamagnetism.
Yes. Diamagnetism is the inherent property of repelling magnetic fields. People usually think of metals and magnets as best friends,
Right, like iron or nickel.
Exactly. Ferromagnetic materials like iron have unpaired electrons in their orbitals. When a magnetic field comes near them, those unpaired electrons spin around and align with the field. That's why a magnet snaps onto your refrigerator.
But copper does the exact opposite. Because its orbital electrons are perfectly paired and canceled out, there is literally nothing to align.
Nothing. It cannot hold a permanent magnetic charge, not even if you drop it to incredibly cold temperatures. It actively rejects the field.
But the rejection isn't just like a passive wall bouncing a field away, right?
Not at all. It's a highly active, dynamic defense mechanism, all thanks to that sea of free-flowing 4s electrons. Copper has the second highest electrical conductivity of any metal on Earth.
I think only silver is higher.
Right. So when an alternating magnetic field hits a piece of copper,
Those free electrons react instantaneously.
they do. The incoming magnetic field physically pushes them, inducing an electrical current. They begin to swirl in these tight, rapid circular paths within the metal. Physicists call these eddy currents.
And here's where the physics gets beautiful. Lenz's law.
Yes. Lenz's law dictates that any induced electrical current will automatically generate its own magnetic field, and the direction of that new field will directly oppose the change that originally caused it.
I always visualize this like a martial artist, specifically like an Aikido master.
Oh, I like that.
Yeah, because if you punch a brick wall, the wall just takes the hit. But in Aikido, the defender doesn't just rigidly block. They take the kinetic energy of the attacker's strike, redirect it, and use that exact same energy to throw the attacker off balance. Copper is basically doing electromagnetic Aikido.
That is a brilliant way to conceptualize it. The incoming magnetic field is the attacker. The copper absorbs that dynamic energy, swirls its electrons into eddy currents, and generates a perfectly matched opposing force field that pushes the attacker away.
It neutralizes the interference, using the interference's own energy.
Exactly. And this isn't just some theoretical quirk. We rely on this diamagnetic Aikido for some of our most critical technology today.
Like invisible fortresses.
Yeah, think about an MRI machine in a hospital. An MRI generates violently powerful, fluctuating magnetic fields just to peer inside the human body. If those magnetic waves leaked out of the room, they would instantly fry every pacemaker, computer, and life support monitor in the vicinity.
And conversely, if outside radio frequencies or electromagnetic noise leaked in, it would corrupt the scan.
Exactly. So architects construct the entire MRI room as a Faraday cage lined with solid copper. The copper's eddy currents actively sense any incoming or outgoing dynamic magnetic interference and instantly generate the exact opposing fields to cancel it out.
It creates a pocket of perfect magnetic silence.
It really does.
The same logic applies to aerospace, right? Like with avionics.
Oh, absolutely. When a spacecraft or a high-altitude aircraft leaves the protective bubble of Earth's lower atmosphere, its electronic nervous system is completely bombarded by dynamic magnetic fields and cosmic radiation.
And if a navigation computer flips a single bit because of a stray magnetic wave, the results are catastrophic.
Fatal. So, the critical avionics are shielded in copper alloys. The metal silently fights off electromagnetic radiation at the speed of light, ensuring the computers keep functioning.
So we have an element forged in the collapsing cores of ancient stars, structured at the atomic level to perfectly conduct electricity, while simultaneously generating a force field against magnetic interference. Which brings us down to Earth.
Moving from the astrophysics of deep space to the geological history of the North American continent.
Yes, we're going to look at what happens when these unique physical properties manifest in a specific, massive geological anomaly, and how ancient humans exploited it in a way that continues to baffle modern science. Let's talk about the Keweenaw Enigma, the prehistoric copper heist.
The scale of this is truly staggering. We are focusing on the Keweenaw Peninsula in Isle Royale, located in the Upper Peninsula of Michigan, just jutting out into Lake Superior.
Geologically, this tiny slice of land is an absolute freak occurrence, isn't it?
It really is. If you go back about 1.1 billion years, the North American continent literally tried to rip itself apart.
The mid-continent rift system.
Right. Massive, unimaginable volcanic activity tore a seam straight through the Earth. Magma rushed up to fill the void, creating enormous, near-vertical tabular veins of basalt. And as hydrothermal fluids moved through these cooling rock layers over millions of years, copper precipitated out.
But the crucial detail here, the thing that makes this place so special, is the purity of that copper.
It is the defining feature of the entire region. In almost every other place on Earth, copper is found as an ore. It's chemically bound to sulfur, oxygen, or carbonates.
So if you dig up copper ore, it just looks like a green or gray rock.
Exactly. To get the actual metal, you have to invent smelting. You have to crush the rock, build a furnace, achieve immense, sustained temperatures, and chemically separate the metal from the sulfur.
Which is a massive technological hurdle for early civilizations.
But in the Kawina, because of the specific chemical makeup of those ancient hydrothermal fluids, they completely lacked sulfur. The copper precipitated as native metal. It was 99.9% pure.
That's insane.
An ancient human could just walk through the forest, see a shining piece of metal sticking out of the dirt, pick it up, and immediately begin hammering it into a knife. No smelting required. The earth had completely pre-refined it.
And the geology of the Keweenaw gets even more violent when we fast forward to about 10,000 years ago. The glaciers arrive.
The Laurentide ice sheet. During the last ice age, an expanse of solid ice up to 2 miles thick moved southward across the continent.
2 miles thick.
Just imagine the sheer kinetic pressure of 2 miles of solid ice grinding against the bedrock. As this planetary-scale bulldozer moved over the Keweenaw Peninsula, it hit those vertical veins of pure copper.
And it just sheared them right off.
It ripped massive, multi-ton chunks of pure metal straight out of the earth, and it carried them. These are known as float copper specimens. They were embedded in the bottom of the glacier or just pushed along in front of it.
And as they traveled for miles, the immense friction of the ice and surrounding granite essentially acted as a giant rock tumbler.
Which is exactly why float copper looks so distinct. When the glaciers finally retreated and melted, they dropped these massive boulders randomly across the landscape. Because they had been tumbled, float copper is characterized by being incredibly smooth and rounded on all sides.
I've seen some of the museum specimens online, and they are mind-boggling. There's a documented float copper boulder that weighs 28 tons.
Yes, a single, solid 28-ton piece of pure metal, smooth like a river pebble, just dropped in the middle of the woods.
But not all the copper was carried away.
Yeah.
Some of it stayed attached, which leads us to lake copper.
Lake copper tells the story of the glacier's passage in a totally different way. The A.E. Seaman Mineral Museum at Michigan Technological University actually houses a 19-ton lake copper boulder that holds a Guinness World Record.
And the piece wasn't carried away.
No, it remained attached to the underlying bedrock, but the sheer force of the glacier knocked it over horizontally onto the bottomland of what would eventually become Lake Superior.
So the glacier just drove straight over it instead of carrying it.
Exactly, and you can literally read that history on the metal itself. The top surface of this 19-ton mass is polished smooth, and it contains these deep, parallel gouges, glacial striations, where the ice dragged harder rocks across its surface for thousands of years.
Oh, wow.
But if you look at the bottom surface, which was pressed into the mud and protected from the ice, it remains sharp, jagged, and rough.
It's like a geological freeze frame.
Yeah.
And these boulders scattered across the landscape became the stuff of legend, right? The Ontonagon boulder is a perfect example of this.
The Ontonagon boulder is a massive piece of float copper that just sat on the banks of the Ontonagon River. Indigenous tribes had known about it and revered it for centuries. But as European fur traders pushed into the Great Lakes in the 17th and 18th centuries, rumors started circulating of a solid copper mountain.
The whispers always get exaggerated.
Always. An English trader named Alexander Henry finally laid eyes on it in 1766 and excitedly estimated it weighed 10 tons.
Which was a bit off.
Just a bit. When the geologist Henry Schoolcraft conducted a proper scientific expedition in 1819, he brought the estimates back down to Earth, guessing it was closer to 1 ton.
Which, to be fair, is still a terrifyingly large piece of solid metal to just stumble upon in the wilderness.
It actually weighed about 1,680 kilograms, and its subsequent history is just peak 19th century American opportunism.
Oh, totally.
A Detroit hardware merchant named Julius Eldred became utterly obsessed with it. He bought it from the local Ojibwe tribe. Then the federal government claimed the land, so he had to buy the boulder again from the government.
He had to buy it twice.
He spent years engineering a system to move it, building a custom railway through dense, unforgiving forest just to drag the rock to navigable water.
He finally gets it on a boat, gets it to Detroit, and starts charging people an admission fee just to look at it.
Until the U.S. War Department showed up, confiscated it, and hauled it off to Washington, D.C. Eldred actually fought a massive legal battle, eventually winning congressional compensation for his stolen rock. Today, the Ontonagon boulder sits quietly in the Smithsonian Institution, mostly out of public view.
That is a great historical anecdote, but the real mystery, the enigma we really need to dive into, predates Julius Eldred and the fur traders by thousands of years. We need to talk about the old copper complex.
This is where the story shifts from a geological oddity to an archaeological impossibility. The old copper complex refers to the archaic Native American societies that inhabited the Great Lakes region.
And we're talking way back.
Way back. Carbon dating of artifacts places their peak activity between roughly 6,000 BCE and 1200 BCE, though some studies analyzing sediment cores actually push the timeline back as far as 8,000 years before present.
These were hunter-gatherer societies. They didn't have agriculture. They didn't have permanent stone cities.
They were nomadic foragers, and yet they orchestrated one of the most extensive and labor-intensive mining operations in the ancient world. When modern surveyors began mapping the Keweenaw Peninsula, they didn't just find a few scratches in the dirt. They mapped over 5,000 distinct prehistoric mine pits.
5,000 pits. And remember, they are digging through bedrock. They don't have dynamite. They don't have steel pickaxes. How do you mine solid rock and metal using only what you can find in a forest?
With unimaginable physical labor and archaic ingenuity, their primary tools were hammerstones. They would walk the beaches of Lake Superior looking for incredibly hard, dense cobbles, usually made of diorite.
And they just smash the rock.
Basically, they would peck a groove around the circumference of the stone, haft it to a thick wooden handle using split roots or vines, and essentially beat the copper out of the living rock.
They also use a technique called fire setting, right?
There is ongoing archaeological debate about the extent of fire setting, but the presence of massive amounts of charcoal in the bottom of these pits strongly suggests it.
How does that work?
The mechanics of fire setting rely on severe thermal shock. The miners would build a roaring fire directly against the rock face containing a copper vein. They would get the rock incredibly hot and then suddenly douse it with freezing water from the lake or a nearby stream.
And the rapid temperature change causes the crystalline structure of the rock to violently contract and shatter.
Exactly. It fractures the surrounding rock, making it much easier to pound away the debris with their diorite hammers to expose the copper. Some archaeologists argue that gathering the immense timber fuel required for this would actually be more labor-intensive than just hitting the rock. But either way, the physical exertion is profound.
Yeah, they dug trenches that followed veins for hundreds of feet and sank vertical shafts up to 20 feet deep, using wooden ladders and bone chisels to extract the metal.
And their expertise didn't stop at extraction. They were highly sophisticated metallurgists, even without smelting.
They mastered cold and hot hammering.
They took these raw chunks of native copper and beat them into an incredible array of tools: spear points, awls, axes, celts, harpoons, and delicate crescent knives. But, if you take a piece of copper and just hit it with a rock over and over, you run into a microscopic physics problem.
The metal gets brittle, work hardening.
Exactly. When you hammer copper at room temperature, you are forcing the atoms to slide past each other. This creates defects in the metal's crystalline lattice, known as dislocations.
So imagine a perfectly neat deck of cards that you can easily slide back and forth. Now imagine bending a dozen cards right in the middle of the deck. Suddenly they don't slide anymore, they get tangled up.
That's a perfect analogy. The dislocations pile up, the metal loses its flexibility, and if you keep hitting it, it just cracks in half.
So how did they get around that?
To solve this, the archaic miners discovered the process of annealing. They realized that if they took their brittle, work-hardened spear point and placed it in a fire, not to melt it, but just to heat it to a dull red glow, something magical happened.
The heat gives the atoms enough energetic vibration to essentially unkink themselves.
They snap back into a perfect, uniform, crystalline lattice. The dislocations are entirely erased. The metal becomes incredibly soft and malleable again. They could pull it out of the fire, let it cool, and continue hammering it into increasingly complex shapes.
They just repeated this hammering and annealing cycle until they achieved a perfect razor-sharp edge.
Yes.
So we have thousands of deep pits, massive, earth-moving, sophisticated fire setting, and advanced annealing metallurgy. They're pulling literal tons of copper out of the ground for millennia. Which brings us to the mathematical brick wall of the Keweenaw enigma, the missing metal.
This is the crux of the mystery. In the 20th century, geological and mining engineers looked at the vast network of 5,000 prehistoric pits. They calculated the volume of rock removed, cross-referenced it with the known density of the copper veins in those specific areas, and arrived at an estimation of how much native copper was extracted by these ancient people.
And the number they arrived at was over 1.5 billion pounds.
1.5 billion pounds. That is an industrial-scale extraction. To put that in perspective, that is roughly the weight of 7 modern Nimitz-class aircraft carriers.
But when we look at the archaeological record,
The ledger doesn't balance. It doesn't even come close. If you went to every museum, university, and private collection in the world and gathered every single ancient copper, awl, bead, and spear point ever found in North America and melted them all down into a single block,
You'd have, what, a few tons?
you would barely have a few tons of metal. It represents less than a fraction of 1% of 1.5 billion pounds.
Which raises an incredibly uncomfortable question for archaeology. How does a rudimentary nomadic society orchestrate the generational extraction of aircraft carriers' worth of metal without leaving behind the massive cities, paved supply roads, or industrial infrastructure we normally assume is required for that level of production?
And more importantly, where did the metal go?
Right. So researchers have proposed several theories to explain the missing copper. Let's walk through them, keeping in mind that none of them fully solve the math. Theory 1. Mother Nature took it back. Erosion and natural loss.
The argument here is that over 5,000 to 8,000 years, things degrade. Copper oxidizes. It reacts with carbon dioxide and water to form malachite, that familiar green crust. Highly acidic forest soils can eat away at the metal. Plus, tools are dropped in lakes, buried in unmarked graves, or simply lost in the woods.
But 1.5 billion pounds of lost tools.
That's exactly why the theory falls short. Yes, soil degrades copper, but the metal doesn't just evaporate. If 1.5 billion pounds of copper degraded in the Midwestern soil, we should be finding massive subterranean layers of copper oxide or enormous degraded caches of tools.
The physical mass has to go somewhere.
And we aren't finding it.
Which leads to Theory 2, the trade networks.
Now, this theory has the most solid archaeological backing. We know for a fact that Keweenaw copper was a highly prized commodity that moved across the continent. Because of its 99.9% purity and unique trace element profile, often containing tiny amounts of native silver, we can actually chemically fingerprint it.
And where does that fingerprint show up?
Everywhere. Artifacts made of unmistakable Lake Superior copper have been excavated from the mounds of the Hopewell culture in Ohio, the Mississippian culture spanning the southeast, all the way down to Florida and out to the Appalachian Mountains.
So there was clearly a massive transcontinental trade network operating via the river systems.
There was, but again, we run into the math problem. Even if we account for every single artifact found at the end of those vast trade routes, it still accounts for a negligible percentage of the mined volume. The trade routes explain the distribution, but they absolutely do not explain the missing mass.
Which opens the door for the fringe theories. Theory 3. The transoceanic Bronze Age supply chain.
This is a highly controversial, persistent theory that is entirely rejected by mainstream academia. Proponents point out that during the Bronze Age in the Mediterranean, roughly 3000 BCE to 1200 BCE empires like the Minoans, Egyptians, and Phoenicians were producing massive quantities of bronze, which, of course, requires copper.
But Europe doesn't have 1.5 billion pounds of easily accessible copper.
Exactly. The theory posits that ancient maritime cultures navigated across the Atlantic, down the St. Lawrence River, and into the Great Lakes, specifically to mine the Keweenaw veins and ship the metal back to fuel the Mediterranean Bronze Age. Some proponents even claim that the isotopic signatures of certain Old World bronze artifacts match Lake Superior copper.
Why does the mainstream archaeological community reject this so fiercely?
Because of the total absence of logistical infrastructure. You cannot orchestrate a transoceanic mining operation of that scale without leaving a footprint. There are no Mediterranean shipwrecks in the Great Lakes. There are no Old World pottery shards, no Phoenician coins, no ruins of way stations, no written records of a perilous journey to a frozen, forested continent.
Extraordinary claims require extraordinary evidence.
And the physical evidence for this simply does not exist.
So we are left with a ghost story. An empty vault, 5,000 deep pits, and no suspects. But when researching this, the thing that gave me actual chills wasn't just the missing metal. It's the fact that the landscape itself seems to be reacting to it. The phenomenon of the shaking grounds.
The Keweenaw Peninsula is geologically haunted. Even today, residents and visitors frequently report experiencing terrifying, unexplained sensory events. They are colloquially known as Baraga booms or Seneca guns.
Describe what happens during one of these events.
Without warning, a massive, deafening, booming noise will echo across the hills. It sounds like subterranean artillery fire. And it isn't just auditory. The ground physically shakes. Windows rattle, and people feel the vibration right through the soles of their feet.
Like a localized earthquake.
That's the logical assumption. But when scientists check the seismographs, nothing. There is zero tectonic fault line activity. The Earth is seismically quiet. Furthermore, these events frequently happen on perfectly clear, cloudless days, completely ruling out atmospheric thunder or lightning strikes.
So what is causing the bedrock to physically boom and shake?
Geologists have several hypotheses. Some suggest cryseisms, or frostquakes, where underground water suddenly freezes, expands, and fractures the rock.
That makes sense.
Others suggest glacial rebound, the continent slowly expanding upward after the heavy ice sheets melted 10,000 years ago. Or perhaps it's the sudden, violent release of ancient gas pockets trapped deep in the rock. But honestly, none of these theories conclusively explain the sheer, localized intensity of the Baraga booms.
And this modern scientific bafflement perfectly mirrors the ancient indigenous oral histories.
Yes, it does. The Ojibwe and other Anishinaabe tribes have deep, reverent oral traditions regarding the copper of this region. They didn't view it simply as a resource. They viewed it as a spiritually charged substance. Their histories speak of thunder beings that resided in the hills and guarded the copper.
And they specifically describe the ground shaking.
The legends describe booming noises emanating from the shaking copper hills. According to the oral traditions, these thunderings were divine warnings, explicitly telling the people to stop digging.
Wow.
Some anthropologists actually suggest that the old copper complex didn't just slowly fade away. They hypothesize that the massive mining operations were abruptly abandoned because the miners were terrified by these violent, unexplained terrestrial warnings.
I mean, imagine being an ancient miner, waist deep in a bedrock pit, slamming a rock against a vein of copper, and suddenly the entire earth beneath you detonates with a soundless earthquake. You drop your hammer and you run. It's an incredible image.
It really is. But there's a profound biological irony to the entire old copper complex. Those archaic miners prized the copper for its physical malleability. They valued its ability to be pounded into a heavy celt or a razor-sharp spear point.
Right.
What they could not possibly comprehend is that every time they held a copper tool, they were wielding a weapon on a completely different, invisible battlefield.
A microscopic battlefield. Which brings us to the next phase of our journey. We are zooming all the way in from the massive scale of a 1.5 billion pound extraction down to the scale of single-celled organisms.
We're looking at copper as a contact killer.
Let's explore the oligodynamic effect.
The word itself gives away its function. It comes from the Greek oligos, meaning few or minute, and dynamis, meaning force or power. The oligodynamic effect is the scientifically observed phenomenon where certain heavy metals exert an intensely lethal biocidal effect on microorganisms, even in incredibly tiny, minute concentrations.
So we aren't talking about dumping a gallon of bleach on bacteria. We are talking about trace amounts of metal annihilating microbes. Walk me through the exact biological mechanism. If I am a bacterial cell, let's say a cell of Staphylococcus aureus, and I land on a solid copper surface, what exactly happens to me?
It is a rapid, catastrophic molecular cascade. When you land on that copper surface, the metal is not chemically inert. Due to ambient moisture in the air, or, the moisture from the hand that just touched the doorknob, the solid copper begins to release free copper ions, charged particles, into the microscopic layer of water surrounding you.
And my bacterial cell just absorbs those ions.
Your cell actively pulls them in, mistaking them for essential trace nutrients. But once those copper ions breach the bacterial cell wall, they act like molecular shrapnel.
Shrapnel.
Yeah, first, they attack the cell membrane itself. They generate intense localized oxidative stress, literally punching microscopic holes in the lipid bilayer. The cell begins to bleed out, losing essential cytoplasm and water.
But the real assassination happens deeper inside the cell with the proteins.
Yes. Proteins are the biochemical engines of life. They construct the cell, they digest food, they replicate DNA. A protein is a long chain of amino acids folded into a highly specific three-dimensional shape. In biology, shape dictates function. If a protein is shaped like a key, it fits a specific lock. If you bend the key, it is useless.
And copper bends the keys.
Violently.
Yeah.
Many critical amino acids contain specific chemical side chains. Thiol groups, which are made of sulfur and hydrogen, and amine groups, which are made of nitrogen and hydrogen. Copper ions have an overwhelming chemical affinity for sulfur and nitrogen. The moment a free copper ion encounters a sial or a metagreen group on a bacterial protein, it binds to it with massive force.
It just rips the hydrogen off and locks itself in.
Exactly. And by physically attaching a heavy metal atom to the side of the protein, the entire three-dimensional structure of the protein warps and collapses. This is called denaturation. The enzyme loses loses its shape and therefore it loses its function.
So it's not just one protein.
No, the copper ions systemically sweep through the bacterium, simultaneously denaturing thousands of critical enzymes. They shut down the respiratory chain, meaning the cell can't generate energy. They bind to the DNA, preventing it from unzipping and replicating. The bacterium suffers complete systemic metabolic failure and dies rapidly.
And this mechanism isn't limited to just bacteria.
No. The research shows that the oligodynamic effect is highly effective against viruses as well. Viruses are essentially just a packet of genetic material wrapped in a protein coat. The copper ions attack those structural proteins, shredding the viral envelope and degrading the viral RNA or DNA inside. It has been proven to destroy highly resilient pathogens like the influenza virus, norovirus, and even HIV on contact.
To really drive the data home on this, there was a fascinating, incredibly elegant microbiology study that was presented at the Regeneron International Science and Engineering Fair, or ISEF.
Yes, that was a great paper.
A student researcher named Whitney Curtis set out to specifically quantify how fast different copper alloys kill lethal bacteria.
It is a beautifully designed experiment that isolated the variable perfectly. She wanted to compare the pure native metal against its two most common historical alloys, brass and bronze. She chose 3 highly dangerous, clinically relevant pathogens to test: E. coli, Salmonella enterica, and the one we mentioned earlier, Staphylococcus aureus, which causes staph infections.
How exactly do you measure the death rate of invisible bacteria on a piece of metal?
You use the Kirby-Bauer disk diffusion method, which is a staple of microbiology. She took agar plates petri dishes filled with a nutrient-rich gelatin and swabbed the entire surface with the bacteria, creating a uniform bacterial lawn. Then she took 13-millimeter solid sterile rounds of pure copper, brass, and bronze and placed them directly in the center of the dishes.
So the metal's just sitting in the jelly and the bacteria are trying to grow around it.
Right. She incubated the plaques to let the bacteria multiply. But as the bacteria grew, the metal rounds were slowly leaching those lethal copper ions into the surrounding agar gel. The ions diffuse outward, creating a chemical gradient.
A kill zone.
Precisely. In microbiology, it is called the zone of inhibition. It is a perfectly clear circular halo around the metal disc where the concentration of copper ions is so high that no bacteria can survive. By measuring the diameter of that clear halo, you can perfectly quantify the biocidal power of the metal. The larger the halo, the deadlier the metal.
And the results were remarkably specific. Pure copper created a mean inhibition zone of 8.06 millimeters. Brass, which is copper alloyed with zinc, was virtually identical at 8.04 millimeters. But bronze outperformed them both by a massive margin.
Yes, the bronze rounds generated a mean inhibition area of 9.89 millimeters.
That is nearly 2 millimeters larger. But in science, you can't just look at a number and say it's better. You have to prove it wasn't a fluke.
Exactly. She applied rigorous statistical analysis, specifically an ANOVA test analysis of variance, to determine if the difference was statistically significant. The resulting p-value was 0.043.
Meaning what for the layman?
Well, a p-value is the probability that the results you saw were just random chance. In clinical science, the gold standard is a p-value of less than 0.05. A p-value of 0.043 means there is less than a 4.3% probability that bronze won by accident. The data conclusively proves that bronze is significantly more lethal to bacteria than pure copper.
Wait, let's look at the mechanics again. If pure copper is the thing killing the bacteria, why does diluting the copper by turning it into bronze make it kill better?
It is a brilliant question. Bronze is an alloy of copper and primarily tin. While the study didn't explicitly map the molecular physics of the alloy, metallurgists hypothesize it is due to a synergistic galvanic effect.
A microscopic battery.
Precisely. When you mix copper and tin at the microscopic level, they have different electrical potentials. When exposed to the ambient moisture in the agar plate, the entire surface of the bronze acts like billions of tiny short-circuited batteries. This galvanic corrosion physically accelerates the release of the copper ions. The bronze pumps the lethal shrapnel into the environment much faster and more aggressively than the pure metal alone.
The incredible thing is that humanity figured this out long before we had agar plates or microscopes. Long before Louis Pasteur and the germ theory of disease, humans were exploiting the oligodynamic effect purely on survival instinct.
Trial and error over thousands of years yielded remarkable public health intuition. In ancient India, Ayurvedic texts recommended storing drinking water in brass or copper vessels. Modern studies have confirmed that doing so actively kills fecal coliform bacteria in the water within hours, preventing massive outbreaks of cholera and dysentery.
In agriculture, you have the Bordeaux mixture.
Yes, a mixture of copper sulfate and slaked lime. It was invented in France in the 19th century and remains one of the most potent fungicides in the world, saving vineyards from devastating blights.
And you see it in maritime history, too,
Oh, definitely. The British Royal Navy revolutionized sea travel in the 18th century by sheathing the wooden hulls of their warships in thin sheets of copper.
to stop the shipworms,
Yeah.
right?
That was the original intent, yes, to stop taro shipworms from boring into the wood. But they quickly discovered an incredible secondary benefit. Biofouling completely ceased. Barnacles, algae, and seaweed simply could not grow on the copper hulls because the constant leaching of copper ions poisoned them on contact. The British ships remained sleek, fast, and maneuverable, while their rivals dragged thousands of pounds of algae through the water.
It even influenced architecture. If you walk through a building constructed in the 1800s, look at the high-touch surfaces, the doorknobs, the thick handrails on staircases, the heavy push plates on swinging doors. They were almost universally made of heavy, unlacquered brass.
The term unlacquered is vital there. Modern architecture often takes a brass fixture and sprays it with a clear coat of polyurethane to keep it shiny and stop it from oxidizing.
But that ruins it.
It perfectly insulates the metal, completely neutralizing the oligodynamic effect. The 19th century architects didn't seal their brass. Those exposed doorknobs functioned as passive, continuous, self-sterilizing systems. Dozens of people could touch a doorknob, depositing bacteria, and the brass would quietly execute the microbes between uses.
Okay, hold on. This is where I have to step in with a major biological reality check.
Let's hear it.
We have spent the last 30 years terrified of antibiotic resistance. The narrative is always the same. We invent a new antibiotic, we prescribe it, the bacteria mutate, the strong survive, and suddenly we have a horrifying superbug like MRSA that is immune to our best drugs. If copper is so lethally effective, and we have been putting it on doorknobs and water pitchers for centuries, why haven't bacteria evolved to resist it? Where are the copper-immune superbugs?
That is the biological paradox that makes copper so immensely valuable. The reason bacteria haven't broadly evolved immunity to copper lies in the fundamental difference between how an antibiotic kills and how a heavy metal kills.
Explain the difference.
Almost all commercial antibiotics are biological sniper rifles. They are designed with extreme chemical precision to target one very specific protein or one singular metabolic pathway inside the bacterium. It is a lock-and-key mechanism. Because the attack vector is so narrow and specific, it doesn't take much for the bacterium to defend itself.
Through a random genetic mutation.
Right. The bacterium slightly alters the shape of its lock. Suddenly, the antibiotic sniper bullet misses, the key doesn't fit, and the bacterium survives and replicates.
But copper isn't a sniper rifle.
No. Copper is a fragmentation grenade going off inside a phone booth. As we established, copper doesn't target one specific enzyme. It attacks the structural integrity of the cell membrane. It induces massive oxidative stress. It binds to the DNA. And it denatures thousands of different cellular proteins simultaneously by attacking any thiol or amine group it touches.
It's an overwhelming systemic multi-front assault.
Precisely. While it is true that certain bacteria can trade plasmids, tiny fragments of DNA that code for efflux pumps, which slightly increase their tolerance by pumping heavy metals out of the cell, it is evolutionarily impossible for a bacterium to simultaneously mutate thousands of its fundamental structural proteins to ignore copper without simply dying in the process.
It would be like trying to evolve an immunity to fire.
Exactly. It would be like a human trying to genetically evolve a biological immunity to being set on fire. The physical destruction is too systemic to mutate against.
Okay, so the grenade analogy makes perfect sense. Bacteria cannot survive the sheer systemic destruction of copper. But that logic leads this directly into a massive, unavoidable biological contradiction.
Which is?
If copper is a biological grenade that indiscriminately shreds cell membranes and destroys proteins, how are you and I currently surviving? Because human beings have copper running through our bloodstream right now. We need it to live. How do human cells survive a metal that obliterates bacterial cells on contact?
This is where we pivot to the sheer elegance and terror of human biology. The answer is that our bodies survive it through an incredibly intricate high-stakes system known as human copper homeostasis.
Homeostasis.
It is a biological high-wire act performed inside every single cell in your body every second of your life. And when that high wire snaps, the consequences are horrific.
Let's walk the tightrope. Let's trace the journey of copper through the human body. How much of this grenade are we actually ingesting?
The average adult absorbs approximately 1 milligram of dietary copper per day. You get it from eating things like nuts, seeds, dark chocolate, shellfish, and organ meats like liver.
1 milligram. A tiny trace amount? But the moment it hits the stomach, the body has to handle it like highly volatile, hazardous waste?
Exactly. Let's look at the import mechanism at the cellular wall of your intestines. When you consume dietary copper, it usually exists in an oxidized state, meaning it is missing 2 electrons. Chemists call this Cu2 plus arum. However, human cells have a very specific import protocol. They only want to absorb copper in a reduced state, Q plus MASH, missing only 1 electron.
So the cell has to modify the metal before it even lets it inside.
Right at the surface of the intestinal epithelial cells, there is a crew of specific enzymes that act as biochemical bouncers. These enzymes include prostate metal reductase, STEAP, and DCYTB. Their sole job is to intercept the C2 plus SCEAP, hand it an electron, and reduce it to Q plus 8.
Once it's prepped, how does it get through the cell wall?
It enters through a highly specialized, dedicated protein channel called CTR1, also known in the medical literature as SLC31A1.
And this isn't just an open door that the copper floats through. The CTR1 transporter actively reaches out and grabs it.
It's a marvel of molecular engineering. At the extracellular opening of the CTR1 channel, there is a specific sequence of 3 amino acids, a his-met-asp cluster.
Histidine, methionine, and aspartic acid.
Yes. The geometry and electrical charge of these 3 amino acids form a perfect molecular catcher's mitt. It is specifically designed to snatch that Q plus ion out of the surrounding fluid, hold it securely, and actively pull it through the lipid bilayer into the interior of the cell.
But the moment it gets inside, the danger spikes.
Drastically. Remember why copper is toxic to bacteria. It creates free radicals and denatures proteins. If a free copper ion is allowed to just float around inside a human cell, it will undergo Fenton-like chemical reactions. It will react with ambient hydrogen peroxide to generate highly toxic reactive oxygen species.
The ROS.
Right. These free radicals act like molecular buzzsaws, tearing apart the cell's DNA and internal membranes.
So the human body's solution is simple. Never, ever let the copper be free.
Precisely. The moment the copper ion emerges from the inside of the CTR1 transporter, it is immediately handed off to a biological police escort. We call these chaperone proteins. The cell maintains a dedicated fleet of these chaperones to ensure the copper is safely sequestered and delivered only where it is needed.
Who are the chaperones and where are they going?
It's a highly compartmentalized system. A chaperone protein called ATOX1 takes the copper ion and ferries it safely to the Golgi apparatus, where it gets folded into other essential enzymes. Another chaperone called CCS specifically delivers copper to an enzyme called SOD1.
And SOD1 is an antioxidant.
Which is a beautiful piece of biological irony. SOD1's job is to hunt down and neutralize toxic free radicals, but it cannot function without a copper atom at its core. The cell uses the very metal that creates oxidative stress to build the machine that destroys oxidative stress.
That's amazing. And then there is the energy requirement.
Yes. A third chaperone, COX17, carries the copper deep into the mitochondria, the energy-producing powerhouse of the cell. The copper is incorporated into cytochrome C oxidase, which is the final enzyme in the electron transport chain. Without copper in your mitochondria, cellular respiration halts, and you produce zero energy.
So we have an import system. We have the highly coordinated chaperone escorts to use the copper safely. But if we are constantly taking in 1 milligram a day, there has to be an exit strategy. The cell will eventually fill up.
To maintain homeostasis and prevent toxic overload, the cell relies on dedicated export pumps. 2 key proteins, ATP7A and ATP7B, manage this efflux. When intracellular copper levels rise too high, these proteins physically migrate from the trans-Golgi network directly to the plasma membrane. They grab the excess copper and forcefully pump it out of the cell, dumping it into the bloodstream, where the liver eventually filters it out and excretes it safely into the bile.
Okay, that is the tightrope. That is a healthy human biology flawlessly juggling a microscopic grenade. But what happens when the genetics fail? What happens when the high wire snaps?
When copper homeostasis fails, the result is a catastrophic, slow-motion physiological collapse known as Wilson's disease.
Let's break down the mechanics of the disease. It starts with a mutation.
It is an autosomal recessive genetic mutation located on chromosome 13. Specifically, it is a mutation in the ATP7B gene.
The ATP7B gene. Wait, that's the code for the export pump we just talked about?
Exactly. In a patient with Wilson's disease, the body absorbs the dietary copper perfectly fine. The bouncers reduce it, the CTR1 catcher's mitt pulls it in, the chaperones ferry it around. But when the cell realizes it has too much copper and tries to take the trash out, the ATP7B pump is either severely deformed or entirely absent.
The door to the incinerator is locked. The garbage truck never arrives.
The copper cannot exit the cell. Furthermore, without a functioning ATP7B pump, the liver is unable to synthesize a vital protein called ceruloplasmin. Ceruloplasmin usually binds to copper in the bloodstream to keep it safe. Without it, and without the ability to excrete copper into the bile, the metal just begins to pile up. Day after day, milligram by milligram, year after year, the copper accumulates in the soft tissues of the body.
And what does that systemic accumulation physically do to the patient?
It is devastating. The liver takes the first hit. The massive influx of toxic copper activates hepatic stellate cells. These cells panic and start laying down massive amounts of collagen scar tissue, leading to severe liver fibrosis and eventually complete cirrhosis and liver failure.
But the liver can only hold so much.
Right. Once it reaches capacity, the copper spills over into the bloodstream and breaches the blood-brain barrier.
The neurological damage described in the medical literature is harrowing.
It behaves like a slow poison in the brain, specifically targeting the basal ganglia, the deep structures that control motor movement and coordination. The oxidative stress from the free copper causes severe demyelination, literally stripping the protective insulation off the nerves and causes the axons to swell and die.
What does that look like clinically?
Patients develop horrifying motor symptoms, severe, uncontrollable tremors. Dystonia, which causes muscles to painfully contract and twist. They lose the ability to speak clearly or swallow. It induces profound memory loss and psychiatric disturbances, often mimicking the symptoms of Parkinson's disease or ALS.
It also systematically destroys the kidneys.
It induces renal tubular epithelial injury, causing the kidneys to leak vital proteins and amino acids into the urine.
But there is one clinical sign that is visually terrifying because you can literally see the metal poisoning the patient.
Yes. The Kaiser-Fleischer rings. Because the copper saturates the entire body, it eventually deposits in the eyes. Specifically, it accumulates in the Descemet's membrane, a deep layer of the cornea. It forms a distinct, visible, dark, rust-brown or golden-green ring circling the iris. You can look a patient in the eye and literally see the heavy metal suffocating them.
For decades, doctors knew that copper caused this damage, but the exact molecular kill switch, the actual mechanism of how the cell died, remained a mystery. Until incredibly recently.
Yes, in 2022, cell biology had a landmark breakthrough. Researchers identified a completely novel, distinct form of regulated cell death. They named it Cuproptosis.
Cuproptosis. How does that differ from the other ways a cell can die? We hear a lot about apoptosis.
Apoptosis is standard programmed cell death. It's highly regulated. When a cell gets too old, it essentially packs up its belongings, breaks down its DNA cleanly, and allows the immune system to consume it. It is an orderly deconstruction. Necroptosis is messy, inflammatory cell death caused by trauma. Ferroptosis is a recently discovered cell death triggered by toxic levels of iron. But cuproptosis operates on a completely different biological pathway, and ground zero is the mitochondria.
Okay, let's zoom the microscope directly into the mitochondria, the powerhouse. What is the excess copper doing in there?
When the chaperones accidentally flood the mitochondria with too much copper, it hijacks the core engine of cellular respiration, the tricarboxylic acid cycle, commonly known as the TCA cycle.
How does it hijack it?
Through a process called lipoylation. Under normal, healthy circumstances, lipoylation is a standard chemical modification. The cell takes a lipid group, a specific type of fat molecule, and attaches it to an enzyme. This lipid acts like a biochemical tether, helping the enzyme interact with other proteins.
But the copper ruins that process.
It forces it into toxic overdrive. The copper targets an upstream regulatory enzyme called FDX1 or ferroxin-1. Under the influence of excess copper, FDX1 goes rogue. It begins forcing abnormal, rapid hyperlipolation on 4 critical proteins within the TCA cycle: DLT, lyase, and LIPT1.
So these 4 essential engine components are suddenly covered in sticky lipid groups. What does the copper do next?
It physically attacks them. The copper ions actively bind to these newly lipoylated proteins. And because copper loves to stick to things, it acts like a biological superglue. It forces all of these crucial metabolic enzymes to clump together, aggregating into massive, toxic, tangled masses inside the mitochondria.
It's literally throwing sludge into the engine gears.
Exactly. And while it is gumming up the proteins, the copper simultaneously begins destroying iron-sulfur cluster proteins, which are the delicate microscopic wires that pass electrons down the energy chain.
So the engine is seized up and the spark plug wires are cut.
Total metabolic collapse. As these toxic protein clumps grow larger, the cell realizes it is dying. It mounts a desperate panic response, flooding the area with heat shock proteins, specifically HSP70, trying to untangle the mess. But it is futile. The endoplasmic reticulum swells massively. The internal folded structures of the mitochondria, the cristae, completely lose their shape. Finally, the mitochondrial membrane simply ruptures, and the cell violently dies.
Okay, I need to pause you here. Let's think through this logically. Human cells have evolved over billions of years. We have a built-in garbage disposal system precisely for this kind of problem, the ubiquitin proteasome pathway.
Right.
Its entire job is to seek out misfolded or clumped-up junk proteins, tag them, and shred them into amino acids.
Yeah.
If excess copper is clumping up proteins, why doesn't the cell just fire up the garbage disposal and clean up the mess before the mitochondria explodes?
That is the most brilliant, insidious part of the entire Cuproptosis mechanism. It is the ultimate biological double-cross. The 2022 research revealed that copper doesn't just stick the TCA proteins together. High intracellular levels of copper actively inhibit the ubiquitin proteasome pathway. The copper chemically deactivates the very enzymes responsible for running the garbage disposal.
Are you kidding me?
It is a coordinated attack. The cell is inside the mitochondria, desperately generating massive amounts of toxic, clumped junk proteins that are suffocating it, and simultaneously, the copper has padlocked the doors to the incinerator. The cell is drowning in its own trash, and its automated cleanup mechanism has been unplugged by the exact same metal causing the trash. That is why cuproptosis is so ruthlessly efficient and rapid once the threshold is crossed.
It is an inside job. It destroys the engine and cuts the brake lines at the same time.
Precisely. And while this mechanism is the terrifying reality for patients with Wilson's disease, understanding it has blown the doors wide open for modern medicine. For decades, we could only treat Wilson's disease with chelators blunt force drugs like penicillamine that bind to copper in the blood and pull it out through the urine. But now that we understand the exact mechanism of FDX1 and lipoylation, pharmacologists are designing highly targeted therapies that can intervene inside the cell, protecting the proteins before they clump.
But it goes even further than that, right? Like with cancer research.
Yes, this is where the assassin becomes our greatest ally. Tumor cells have massive energy requirements, and their mitochondria operate differently than healthy cells. Oncologists are currently researching how to weaponize cuproptosis.
Weaponize it how?
If we can develop a drug that intentionally delivers a lethal payload of copper only into the mitochondria of a cancer cell, we can intentionally trigger this explosive cell death. We can use the biological grenade to eradicate tumors from the inside out, utilizing a pathway that the cancer has absolutely no defense against.
Turning the ancient assassin into a highly directed, microscopic weapon. That is unbelievable. And it perfectly bridges us to the final leg of our deep dive. We have explored copper in the past, and we've journeyed deep into its biological mechanisms inside our cells. Now, we're going to look at how humanity is actively leveraging copper's unique atomic properties, the exact properties forged in the stars, to build the absolute bleeding edge of human engineering.
We are transitioning from biology to physics. We are looking at the hottest and coldest environments humanity has ever engineered.
Let's start with the heat. We are trying to build a star on Earth, nuclear fusion. Specifically, we are looking at the EU-DEMO fusion reactor project. And the prime candidate for one of the most critical structural components in that reactor is a copper alloy called QCr-Zirconium. Copper chromium zirconium.
The engineering constraints of a fusion reactor are almost impossible to comprehend. Inside the reactor core, you are confining a plasma of deuterium and tritium that is burning at over 100 million degrees Celsius. Obviously, no physical material in the universe can directly touch a 100 million degree plasma without instantly vaporizing.
The plasma is contained by massive, invisible magnetic fields.
Yes, but the reactor walls still have to deal with the intense radiant heat, the exhaust of helium ash, and the barrage of subatomic particles. The most punished component of the entire reactor is called the diverter. It sits at the bottom of the magnetic containment vessel and acts as the exhaust pipe and heat sink.
And the diverter is facing conditions that literally mimic the birth of copper.
The irony is profound. The diverter is subjected to immense cyclical thermal shocks and relentless high-energy neutron irradiation. The exact same free neutrons that slammed into iron nuclei to forge copper in a dying star billions of years ago are now being fired out of the fusion plasma directly into the reactor walls.
So why choose QCRZ for the heatsink? Why not steel or titanium?
Because of the thermal conductivity we discussed earlier, you need a material that can pull the massive heat away from the plasma-facing surface incredibly fast, transferring it to the cooling water behind it. Copper is the master of thermal conduction. If you use steel, the heat wouldn't move fast enough, the surface would melt, and the plasma would be contaminated, killing the fusion reaction.
But pure copper has a fatal flaw here.
It is far too soft. Under the structural stress of the reactor, the pressure of the cooling water, and the thermal expansion, pure copper would quickly warp, deform, and rupture. You need the thermal conductivity of copper, but you need the high-temperature yield strength of steel.
Which is why you add the chromium.
This introduces a metallurgical mechanism called precipitation hardening. When you alloy a tiny amount of chromium into the copper matrix, the chromium atoms clump together to form microscopic, incredibly hard particles precipitates scattered evenly throughout the copper crystal lattice.
Going back to our deck of cards analogy,
Yeah.
the copper atoms want to slide past each other and bend.
But the hard chromium precipitates act like tiny steel pins driven vertically through the deck of cards. They lock the sliding layers in place. They vastly increase the metal's strength, preventing it from deforming even when the temperature spikes.
But metallurgy is a balancing act. The research notes point out a specific problem with chromium.
Yes. If the chromium precipitates clump together too much, if they become coarse and large, they act as stress concentrators. The metal becomes strong, but brittle. Under the constant thermal cycling of a fusion reactor, a brittle metal will develop microcracks and suffer fatigue failure.
Which is where the zirconium saves the day.
Zirconium is the stabilizing agent. Adding just a fraction of a percent of zirconium refines the grain structure of the alloy. It chemically restricts the chromium from forming large clumps, ensuring that the precipitates remain at the optimal nanoscale size. It improves the ductility of the metal, its ability to flex and bend slightly without snapping, and drastically increases its resistance to thermal fatigue and neutron embrittlement.
So you have the perfect recipe. Heat conduction from the copper, locked-in strength from the chromium, and flexible stabilization from the zirconium. But the engineering doesn't stop at the recipe. You can't just mix these three metals in a pot, pour it into a mold, and stick it in a fusion reactor.
The material science required to force these elements into their perfect atomic arrangement requires incredibly complex, precise heat treatments. The literature details processes like SAA and SACWA.
Walk us through what SAA actually is.
SAA stands for solution annealing and aging. It is a multi-step thermal manipulation. First, they take the cast alloy and heat it to a blisteringly high temperature, typically around 980 degrees Celsius. This is the solution phase. At this temperature, the chromium and zirconium atoms completely dissolve and disperse evenly into the solid copper matrix like sugar dissolving into hot tea.
And you trap them there.
By rapidly quenching the metal in water, this freezes the atoms in place before they can clump together. But the metal is still too soft, so they move to the aging phase. They heat the metal back up, but only to a moderate temperature, exactly 460 degrees Celsius, and hold it there for hours.
And what is happening at 460 degrees?
That exact temperature provides just enough thermal energy for the dissolved chromium and zirconium atoms to slowly migrate through the lattice and form those microscopic nanoscale precipitates we talked about. By strictly controlling the time and temperature, engineers dictate the exact size and distribution of the strengthening pins.
And SACWA takes it one step further.
SACWA adds a crucial physical step: cold working. Between the high-temperature solution phase and the lower-temperature aging phase, they physically deform the metal at room temperature, perhaps by rolling it or stretching it.
Wait, I remember this from the ancient miners. Cold hammering creates dislocations. It tangles the deck of cards.
Exactly. The modern aerospace engineers are using the exact same physical mechanism the archaic hunter-gatherers used 8,000 years ago. They intentionally introduce a dense network of dislocations into the lattice. Then, when they perform the 460-degree aging phase, the nanoscale precipitates preferentially form directly on those tangled dislocations, locking them permanently into place. The result is a superalloy with astonishing yield strength that still conducts heat like pure copper.
And it needs every ounce of that strength. because the operational window for this metal inside the diverter is razor thin.
Under intense neutron bombardment, the QCRZ alloy must be maintained between roughly 150 degrees Celsius and 350 degrees Celsius. If it gets hotter, it overages, loses its strength, and melts. If it gets colder, the radiation damage makes it instantly brittle. Balancing the heat of a miniature sun to keep the walls exactly within that 200-degree window is one of the pinnacle engineering challenges of our species.
That is the ultimate macroengineering, taming the plasma of a star. But copper's future isn't just in massive, blazing hot fusion reactors. It is also at the absolute coldest, most delicate, microscopic frontier of physics, quantum computing.
We are transitioning from the brute force of thermal mechanics to the delicate, almost ghostly manipulation of quantum states. And at the center of this research is a molecule known as copper phthalocyanine, or Cuproptosis.
This is perhaps my favorite detail in this entire deep dive, because copper phthalocyanine sounds like an incredibly exotic million-dollar laboratory chemical. But what is it in everyday life?
It is utterly mundane. It is a cheap, abundant, organic blue pigment. It is used in mass-market paints. It is used to color plastics. And famously, it is the exact blue dye used by the Bank of England to print the blue 5-pound note.
A literal piece of pocket change. But to researchers at the London Center for Nanotechnology, this blue dye is the holy grail. It is a low-cost organic semiconductor that might finally make quantum computers commercially viable.
To understand why a blue dye is revolutionizing computing, we have to establish what a quantum computer actually does. Classical computers, the ones we use every day, process information using bits. A bit is a physical transistor that is either on or off, a 1 or a 0. It is binary.
But a quantum computer uses qubits.
Qubits operate under the bizarre rules of quantum mechanics. Thanks to a property called superposition, a qubit does not have to be just a 1 or a 0. It can exist in a state where it is both a 1 and a 0 simultaneously.
And because it can be multiple things at once, the processing power scales exponentially.
A classical computer solving a complex maze has to run down every single path, one by one, until it finds the exit. A quantum computer in superposition essentially walks down every single path in the maze simultaneously and finds the exit instantly. This multidimensional processing gives them the potential to solve problems, like perfectly modeling pharmaceutical molecules, optimizing global logistics networks, or instantly cracking modern cryptography that would literally take a classical supercomputer the entire lifespan of the universe to calculate.
Okay, so the math is godlike. What is the engineering roadblock?
Fragility. The state of superposition is unbelievably delicate. It is easily destroyed by a process called decoherence. If any outside energy, a slight rise in temperature, a stray magnetic field, even a microscopic physical vibration interacts with the qubit, the superposition collapses immediately back into a boring classical 1 or 0.
The decay time.
Yes. Most modern quantum computers use exotic, superconducting metals that have to be cooled to near absolute zero, colder than deep space, just to maintain superposition for a fraction of a millisecond. It is a logistical nightmare. The goal is to find a qubit with a long decay time that doesn't require a multi-million-dollar cryogenic laboratory to function.
Enter the blue dye on the 5-pound note. Copper phthalocyanine.
The researchers discovered that the copper atom sitting at the dead center of this pigment molecule can hold a quantum superposition for a shockingly long time.
Okay, I have a massive pushback here. A chemistry contradiction based on everything we talked about in the first 20 minutes.
Let's hear it.
You explicitly explained that copper atomic number 29 has completely paired electrons in its third orbital, making it diamagnetic. But to have a qubit, you need a quantum spin state to manipulate, which requires an unpaired electron. If all the inner electrons are paired and the outer one floated away in the sea, how does Cupid have a spin to act as a qubit?
That is a phenomenal catch, and it highlights the exact reason Cupix is an organic molecule and not a solid chunk of metal.
Yeah.
In solid copper, yes, you have the argon 3d10 force 1 configuration with the paired d electrons. But inside the copper phthalocyanine molecule, the copper atom is chemically bonded to nitrogen atoms. In order to form those bonds, the copper atom gives up 2 of its electrons. It becomes an ion, C2+.
It loses the outer 4s electron, and it loses one of the 10 third electrons.
Exactly, it becomes argon 3d9. Because there are only 9 electrons in the d orbital, one of them suddenly finds itself without a dance partner. It is a lone unpaired electron, and the spin of that single unpaired electron, whether it is spinning up, spinning down, or in a superposition of both, is the qubit.
That perfectly solves the contradiction. But why is this specific molecule so good at protecting that superposition? Why doesn't it just collapse like the exotic superconductors?
It comes down to its organic architecture. In COPEC, that central copper ion is suspended in the middle of a massive, rigid, ring-like structure made of carbon and nitrogen atoms.
The silicyanine ring.
Yes. That rigid organic ring acts as a microscopic shock absorber. It physically shields the copper's unpaired electron from outside thermal vibrations and stray magnetic noise. It isolates the electron, allowing it to maintain its delicate spin state, its superposition, for dramatically longer periods than we previously thought possible.
And the practical engineering benefits of this are off the charts.
They are revolutionary. Because Q-Pix is a dye, we already know how to manufacture it cheaply at industrial scales. We don't need exotic vacuum chambers. It strongly absorbs visible light, which means engineers might be able to use standard off-the-shelf lasers to write and read data directly to the electron's spin. And because it is a stable organic molecule, we can easily process it into thin films using standard semiconductor manufacturing techniques.
We can print quantum processors the same way we print modern microchips.
Exactly. Chemists can even tweak the outer edges of the carbon ring to fine-tune the magnetic and electrical properties of the copper atom at the center, customizing the qubit for specific tasks.
I just have to pause and marvel at the profound juxtaposition we have arrived at. I want to make sure the listener is fully grasping the cosmic scale of what we were talking about.
It is the ultimate testament to the hidden depths of the physical world.
The exact same element, copper, atomic number 29, forged in the catastrophic collapse of an ancient star. It is currently being engineered to act as the ultimate heat shield, containing the 100 million degree plasma of a miniature sun in a fusion reactor. And simultaneously, an ionized version of that exact same atom is sitting in our wallets right now, acting as the blue dye on a piece of paper currency, quietly maintaining the delicate, freezing quantum superpositions required to unlock multidimensional computing power.
It spans the absolute extremes of human endeavor. The hottest plasma, the coldest quantum states, the deepest history, and the most intricate biology.
Unbelievable. Okay, let's bring this all together. Let's trace the full arc of the journey we just took.
We started in the violent furnaces of the cosmos. We watched free neutrons bombard iron nuclei to forge copper, and we saw how modern astrophysicists use supercomputers and 3D non-LTE models to map the chaos of those stellar atmospheres.
We zoomed into the atom itself. We saw how the paired third electrons and the free-flowing 4s electrons C make copper diamagnetic. It isn't just conductive, it's an electromagnetic Aikido master, using dynamic eddy currents to actively cancel out interference and protect our MRI machines and spacecraft.
From the atom, we dropped down to the Quinault Peninsula 1.1 billion years ago. We witnessed the mid-continent rift tearing the Earth apart and the 2-mile-thick glaciers grinding 28-ton float boulders across the landscape.
We stood at the edge of the 5,000 pits of the old copper complex. We watched archaic hunter-gatherers use fire setting and the microscopic manipulation of crystalline dislocations through annealing to build an ancient empire. An empire that extracted 1.5 billion pounds of pure metal, only to vanish into the mist, leaving behind an empty vault and the haunting, unexplained baraga booms of the shaking earth.
We then turned the microscope on the oligodynamic effect. We watched copper act as a biological grenade, aggressively leaching ions that punch through bacterial cell walls and violently denature critical enzymes by binding to their thiol and amamine groups. We saw the statistical proof of bronze's galvanic lethality and why bacteria can never mutate to survive it.
And we learned the horrifying paradox of how our own bodies navigate that lethality. The perfect high-wire act of the CTR1 catcher's mitt and the dedicated chaperone proteins.
And the devastation when the ATP7B export pump fails in Wilson's disease. The terrifying 2022 discovery of Cuproptosis, how the assassin forces FDX1 to hyperlipoylate the TCA cycle, aggregating a massive pile of toxic junk proteins inside the mitochondria while simultaneously cutting the brake lines and deactivating the cell's own garbage disposal system.
Finally, we look to the future. The QCrZr superalloy, relying on nanoscale chromium, precipitates to survive the neutron bombardment of a fusion reactor, and the copper phthalocyanine molecule, using its rigid organic ring to protect the quantum spin of a single unpaired electron, unlocking the multidimensional math of tomorrow.
It is a single material that connects the origins of the universe to the absolute bleeding edge of human technology, passing through the mysteries of our ancient history and the delicate machinery of our biology along the way.
Which brings us back to where we started. I asked you to look at a penny, or to hold a piece of electrical wiring, and to realize it is an alien artifact. And I want to leave you, the listener, with a final provocative thought to mull over as you go about your day.
What is that?
Consider the sheer, quiet power of the mundane. If a material as basic as copper, something so completely ubiquitous that we literally use it for loose change, something we coat the bottoms of boats with and make standard plumbing pipes out of,
Hmm.
if a material that painfully ordinary harbors the ability to dictate ancient human evolution, to orchestrate the explosive death of a cancer cell from the inside out, and to unlock the multidimensional math of the quantum realm, what other seemingly mundane materials are sitting right in front of us? What is sitting on your desk, in your kitchen cabinet, or in the dirt outside your front door, just waiting for us to ask the right questions and discover its hidden superpowers?
It forces you to realize that nothing in the physical world is truly ordinary. We are just waiting for the science to catch up to the reality of what we are holding.
Suddenly, that muddy water isn't just murky, it's where the real magic is hiding. Thank you for taking this deep dive with us. You are now armed with a completely transformed understanding of the physical world around you. Seriously, go look at a penny. Really look at it. We will see you next time.